In this lesson, we're gonna focus on rotating vessels. Now, this topic still covers the concepts in the relative equilibrium of liquid masses. However, so that we can proceed with the application directly, I will not be deriving the formula. Instead, I will just give directly the formula for H. Now, let's say we have this cylindrical vessel which is filled with water to a certain depth. So this is, let's say, Y. And then the depth at which there is no water, let's call that D. And so this portion, that's filled with air. Now this is the initial condition wherein our vessel is not rotated. So the water line will remain level or horizontal. And so again, this is the original water level. And then if we are to check the volume of air, we have pi r squared multiplied by D. This is just the cylindrical volume wherein our cross-sectional area is pi r squared and our height is the depth D at which there is no water. Now what if I'm gonna rotate this vessel about the center point? This is what's gonna happen. The water line will actually now be a curved surface. And so, if we are to show the original water level, this is it. The depth is actually D, this one. However, since we rotated this vessel, this will now curve right here. And so this figure shows the condition at which no water is spilled, but it is not still on the verge of spilling. Now sir, when will water be on the verge of spilling? It happens when it meets this condition. Let's rotate the vessel faster. This is what will happen. And so again, if we are to show the original water level, we have this one. But this is now the new water level, but the surface is now curved. Now recall that the original volume of air was pi r squared multiplied by D. And so when the vessel is on the verge of spilling, then this volume, the volume of the air, that should equal this volume, because this is the last point at which this volume is not exceeded. And so we have to recall that the volume of the air, or this paraboloid, this one right here, that's half of the circumscribing cylinder. Now sir, what do you mean by circumscribing cylinder? Notice that the vertex of this new surface is right here. And then the highest points of the new surface are right here. And so if we will draw this line, a vertical line, right here and also right here, and then let's connect this to the center, as well as this one, the volume of this part divided by 2, that's the volume of the paraboloid. Again, this is the circumscribing cylinder, because it covers the vertex and our highest points. And so what's going to be the volume of the paraboloid? This is what we are interested in. Now for this condition, the volume of the paraboloid will be pi r squared multiplied by 2D, which is the height, divided by 2. Now sir, why are we dividing by 2? We are dividing by 2 because again, the volume of the paraboloid, which is in this case, the part filled with air, that's half of the circumscribing cylinder. And so this is the volume of the circumscribing cylinder, and we are taking half of it. And so simplifying this, we have 2 will cancel. This will be pi r squared multiplied by D. And so notice that this volume is equal with this initial volume. And so again, this is the last point at which the initial volume of air will not be exceeded, because it will now be equal. And so recall that to solve H, this distance, if we are given the speed of rotation, we have H is equal to omega squared times r squared divided by 2g, where W is the speed of rotation in rad per second or radians per second, R is the radius of the cylinder, and then g is the gravitational constant, which is 9.81 meter per second squared. And so these are our variables. Now we also have another concept wherein the distance between the vertex to the original water level is equal to the distance between the original water level to the highest point on the new surface. And so what does it mean? What this means is when there is no water spilled, then the distance from the vertex to the original water level, which is this point, again, if we are to show the original water level, we have this one. This is the original water level, and then these are the highest points on our new surface. And so if the distance from the original water level up to the highest point is D, then the distance from this point up to this point must also equal D, because this distance and this distance must be equal. So this is also another important concept. By the way, we need to change this one. This is actually our H. And so if this distance is, let's say, A, then this distance must also be A, because this was the original water level, and so from the vertex up to here, that's gonna be the same distance from the highest point, which is aligned to this one, up to the original water level. So these distances, they are equal. And so try to remember this concept. Now let me just erase this. And then what's gonna describe this condition is, this is the figure which shows the situation at which no water is spilled, but it is already on the verge of spilling, because now the new water surface already touches the tip. Now what if we're gonna increase the speed of rotation? What's gonna happen? If we'll increase the speed of rotation, since the speed of rotation, or omega, is in the denominator, then it will be directly proportional to the height h. And so if we are to increase w, h will also increase. And so if we'll rotate this faster, this is what's gonna happen. The height h, which is this height, will actually increase. And so this volume already exceeds the original volume of air. And so the difference in this volume minus the original volume of air, that's gonna be the water spilled. Now, if you are to show the water line at which no water is spilled, we have this one. This was the condition at which no water was spilled. Now, by the way, the height at which no water is spilled is equal to 2d, where d is the height that contains no water in our initial condition. And so what will be the volume spilled? The volume spilled is actually this volume. If we are to color that, this portion, it will define the water spilled. And so I hope this is clear. Now I can still increase the speed of rotation such that the vertex of this parabola will just touch the center at the base of the cylinder. And so if we are to show that, this is what happens. And so here, the vertex is just at the center of the base of our cylinder. And so for this condition to happen, h must be equal to the height of the cylindrical vessel. And so here, what's gonna be the water spilled? If we are to show the paraboloid at which water is on the verge of spilling, we have this figure. Let's show this. This is the paraboloid. And so the volume spilled is this volume. If you are to get this one, this is the volume spilled. And so this is another major consideration. However, if we are to increase the speed of rotation such that h will exceed the height of the cylindrical vessel, our vertex will now be below the cylindrical vessel. And so if you are to show that, this is what happens. The vertex is now below the cylinder. And so for this situation, our h will now be this distance. This is h. And then to show the water line at which no water is spilled, we have this paraboloid. Now sir, why are we not including this? This isn't included because that's just an imaginary paraboloid. Since this shaded area, that's the total volume of air. And so to solve this one, what we are going to do is, for the volume spilled, which is this shaded area, we have the volume of the largest paraboloid, which is this total paraboloid, minus the volume of the paraboloid on the verge of spilling, which is this volume, so volume no spill, and then minus the small paraboloid at the bottom. And so again, the largest paraboloid minus this one, that will be the total volume spilled. And so I hope that's clear. And so for you to better understand the topic, let's try to solve the following problems. Now we have a cylindrical vessel that has a diameter of 0.6, and then if the height of the cylindrical vessel is 1.3 and it is filled by water to a depth of 1 meter, let's determine the following. For letter A, we need the distance between the lowest point of the water level when omega is 50 rpm or revolutions per minute toward the original water level. Now once we are to rotate this vessel, we now have this figure. This is now the original water line or original water level, but then our h is gonna be, let's also change this one. This is now our h. And so to solve h, again, we have the formula h is equal to w squared r squared divided by 2g. However, we need omega to be in radians per second. However, since in letter A, the given is in revolutions per minute, then we need to convert this. And so to convert that, we have 50 rpm. Now first, let's convert revolutions. Now for 1 revolution, that's equal to 2 pi in radians. And then to convert minutes into seconds, we have, for 1 minute, we have 60 seconds. And so this will cancel, and also this one. And so omega will be 50 times 2 pi divided by 60. This gives us 5.23 or 236. So 5.236 radians per second. This is now what we'll use. So we have h equal to 5.236 rad per second and then squared multiplied by r squared, which is the radius of our container. So that's gonna be 0.3 meters because the diameter of the vessel is 0.6 meters and then half of that is the radius, which is 0.3 meters. so times 0.3 meter and then squared, divided by 2g, which is 2 times 9.81 meter per second squared. And so second squared here will cancel, and also m. But since we are squaring this in the numerator, then we are left with 1m, which is going to be the unit of our height. And so we have h equal to 5.236 squared times 0.3, also squared, divided by 2 times 9.81. So this gives us 0.126. And so if this is 0.126 meters, then the distance from the lowest point of the water level toward the original water level will be half of this. Because again, this distance and this distance are equal from our concept. And so 0.126 divided by 2, this gives us 0.06 or 0.63. So 0.063 as well as this one. And so our answer for letter A is this value. So 0.063, this one. And so just to recall, the distance between the vertex to the original water level is equal to the distance between the original water level to the highest point on the new surface. And so we're going to move on to letter B. The question is now, what is the value of omega such that no water is spilled but on the verge of spilling? Now let me just change the wording. And so to continue, so that no water is spilled, we know that H must be equal to 2D, because if this is D, then this is also D for our conditions in which no water is spilled. And so again, the total height of the vessel is 1.3 meters, and then the depth of water from the original water level, that's 1 meter. So this is 1 meter, and so the distance D will be 1.3 minus 1 meter. And so the depth at which there is no water for the initial condition, that's gonna be 0.3 meters. And so on the verge of spilling, we have H is equal to 2D. Again, this is explained earlier in the relationships of the volume of air. And so we have omega squared times r squared over 2G. For H, we're gonna substitute 2D. And so this is now 2 times 0.3 meters. This is equal to W squared, which is unknown, times R squared, in which our R is, again, 0.3 meters, half of this, divided by 2 times 9.81. And so solving omega, we have, by the way, for the purpose of simplification, let me just call this W. So 2 times 0.03 equals x squared times 0.3 squared divided by 2 times 9.81. This gives us 11.44. So we have W equal to 11.44 radians per second. However, since we want the result in RPM, we need to convert this. Now we have 11.44 radians per second, and so for 1 revolution, we have 2 pi radians. And then for 60 seconds, we have 1 minute. And so this is now 11.44 times 1 over 2 pi multiplied by 60. This gives us 109.24. So 109.24. And then this is now revolutions per minute, or simply RPM. So 109.24 RPM. And so let's move on to letter C. This is what will happen when W is equal to 120 RPM, what is the amount of water spilled? Now, by inspection, there is already water spilled when the rotational speed is 120 RPM. Now, this is because this rotational speed exceeds this one. Now again, this is the condition for no spillage at the maximum. And so if you will exceed this value, then there will be water spilled. And so this is going to be our figure. By the way, to determine if it's right here or at the bottom or just at the tip, you need to solve H. Now let's try to solve H. We have 120 RPM, which will convert to radians per second. So we will multiply this by 2 pi over 60. Again, this is to convert revolutions into radians, and this is to convert minutes into seconds. So we'll square this whole expression times r squared, which is 0.3 squared, divided by 2g, 2 times 9.81. Now solving H, we have 120 times 2 pi over 60 squared times 0.3 squared divided by 2 times 9.81. This gives us 0.72. And so this height still doesn't exceed the total height of the vessel. And so that's why this is just above the base of the cylinder. And so that's how you can check. However, if we are to show the water line at which no water is spilled, then we have this. Again, the height at which no water was spilled was 0.6 meters, or 2 times 0.3. And so now, the volume spilled is this volume, the one we are shading in red. And so this volume will be the volume of the big paraboloid minus the volume of the smaller paraboloid. And so we have the volume spilled, which is the volume of the bigger paraboloid minus the volume of the paraboloid on the verge of spilling. So V, no spill. So this is gonna be, recall that the volume of the paraboloid is equal to half of the volume of the circumscribing cylinder. So for the bigger one, this is the cylinder it circumscribes. And so this total volume will be pi r squared, in which our r is 0.3, multiplied by 0.72, which is the height of this cylinder. So 0.72, but we're only gonna take half of it. So this is divided by 2. And then this is minus pi times 0.3 squared multiplied by the height, which is 0.6 for this volume. And then we'll divide this by 2. By the way, this is the circumscribing cylinder for the smaller one, which is why we used this volume. So we have pi times 0.3 squared times 0.72 divided by 2 minus pi times 0.3 squared times 0.6 divided by 2. This gives us 0.01696. So we have 0.017, and this is m cubed. And so this is our answer. And so let's now solve letter D. Let's try to rotate the vessel faster. We now have this condition. Now for letter D, we are to find the speed at which the vessel must be rotated in revolutions per minute such that the depth of water at the center of the base of the cylinder must be equal to 0. And so if you see this kind of wording, it just refers to this condition wherein there is no depth right here. So depth equals 0. And so this question is just gonna be easy because we already know h. Now since the total height of the cylinder is 1.3, then if the vertex of the paraboloid will just directly touch the base, then that means that our h is equal to 1.3 meters, or the total height of the cylindrical vessel. And so for this question, we have 1.3 meters. This is equal to w squared r squared, which is 0.3 divided by 2g. And so solving w, we have 1.3 equals x squared times 0.3 squared divided by 2 times 9.81. This gives us 16.83. So w equals 16.83, but this is still in rad per second. We need to convert this. And so we have w equals 16.83 rad per second multiplied by 60 divided by 2 pi. And so this value multiplied by 60 over 2 pi, this is our w, which is 160.76. And then this is RPM. This is our answer. Now, this value of the rotational speed is for this condition wherein the vertex is located right at the center. And so what happens if I'm going to increase the rotational speed? So let's say I'm going to use 165, or let's just consider the question in letter E in which omega is now 200 RPM. Now since this is greater than this value, then our h will now exceed the height of the cylindrical vessel. It's going to be somewhere here. This is going to be our h. And so to illustrate that, we actually have the following figure. This is what will happen. Now if we are to solve h, then by common sense, it will be greater than 1.3. So solving h, we have 200 RPM multiplied by 2 pi over 60, and then squared times r squared, which is 0.3 squared, divided by 2 times 9.81. So solving h, we have 200 times 2 pi over 60 squared times 0.3 squared divided by 2 times 9.81. We have 2.012. So this is 2.012, which already exceeds 1.3 meters. So that's why the vertex is already below the base of the cylinder. And so let me just erase this one. For the volume spilled, we need to show first the paraboloid for which water is on the verge of spilling. And so if I am to show that, we have this figure. And so by inspection, this is going to be our volume spilled, which was explained earlier. And so again, our volume spilled is the volume of the largest paraboloid minus the volume of this paraboloid. So volume, let's just use V for no spillage, and then minus the small paraboloid at the bottom. So V smallest, or let's just use V bottom. And then let's just say this is the volume of the whole paraboloid. Now again, the volume we are considering are the volumes of the paraboloid. And then recall that the volume of the paraboloids are equal to half of the volume of the circumscribing cylinders. And so for the whole paraboloid, which is this paraboloid, this is going to be our circumscribing cylinder. We have this point, and then we'll extend that up to here and up to these points. And so that volume will be pi r squared, which is, for this cylinder, the radius is 0.3. So pi times 0.3 squared multiplied by h, which is 2.012 for the total height. And then we'll divide this by 2. And then we're going to subtract the volume for no spillage or on the verge of spilling. So that's going to be pi times this height is again 0.6. So that's going to be pi times the radius squared multiplied by the height, which is 0.6, divided by 2. However, notice that for this small paraboloid, we can't directly identify the dimensions of our circumscribing cylinder. Now, this is because this is our vertex, and then these are our highest points. And so we actually have this circumscribing cylinder. And so let's say that this is the radius, which we'll label as x. Now, let me use another color. Let's say this is x, and also this distance, that's going to be the radius of our circumscribing cylinder, while this is going to be the height, which we'll label as y. Now let me just change this variable. Let's just make this h of cylinder, or hc. Now our x will remain unknown. However, we can solve y by using this value. Now notice that y is just the height minus 1.3. And so this distance will be 2.012 minus 1.3. So that's going to be 0.712. So this is 0.712. And so for this volume, we have minus pi times the radius x and then squared multiplied by 0.712 divided by 2. However, we're still gonna solve x. Now how can we do that? Let's try to relate this parabola with the whole parabola, because their vertices are located at the same point. And so we can just use ratio and proportion, but we'll consider the squared property of a parabola. And so recall that for y, we need to relate this with x squared. This is used for functions with curves that are of the second degree. So we have y over x squared for this one, this condition, and then we're gonna relate this with the total height, which is 2.012 divided by the radius squared, because for this large parabola, our horizontal distance from the vertex up to this point, that's just gonna be equal to the radius. This radius is the radius of the cylindrical vessel, so this is r squared. However, since we already know r, which is half of this, then this is 0.3. And so solving x, we have, by the way, our y is also this value, 0.712, this one. So 0.712, we can now solve x. So we have 0.712 divided by x squared. This is equal to 2.012 divided by 0.3 squared. And so we have 0.178. So x equals 0.178. And so we now have a value for this. This is now going to be 0.178 and then squared. And so solving that, we have, let's just actually move this expression, these expressions. Let's factor them out. For the first two terms, we have pi times 0.3 squared divided by 2 multiplied by 2.012 minus 0.6. Again, we are just factoring this out because this is common. And then minus pi times 0.178 squared times 0.712 divided by 2. This now gives us 0.164. And so the volume spilled is 0.164 m cubed. So this is our answer. And so this pretty much sums up everything you need to know about rotating vessels. And so I hope this video helped you.